Good morning, everyone. My name is Sébastien Henry. I'm very happy to be here virtually with you today to present the paper Protecting Against Website Fingerprinting with Multihoming. This is joint work with Ginés Garcia Viles, Pablo Serrano, Albert Banks, and Patrick Tiran. So as the title hints, we're going to talk about website fingerprinting. So I'm first going to say a few words about this. So this won't come as a surprise to any of you here that internet service providers, ISPs, can see all of our communications. So if a client is trying to access Google, the ISP will see the source and destination of the packets, even if the traffic is encrypted with HTTPS, for example, and the ISP will know that the client is accessing Google. And for Google with encrypted traffic, this might not reveal a lot of information about the client, but if, for example, the client accesses the website of an oncologist, the ISP will also know it, and this reveals much more information about her health in this case. And overall, knowing the browsing history, which websites a client accesses, enables an ISP to know a lot about the client, the private life of the client. And this is something that ISPs can sell to third parties, for example, and there are a couple of newspaper articles here as early as 2007 and also more recently in 2017, 2019, that present evidence that ISPs sell this information, the browsing history of their client, to third parties that can use this to know much more about the private life of their client. And these third parties can be, for example, health insurance that can use this information to know about the health of the client and for example, to deny coverage to clients based on this information. And in some countries, this has other critical consequences. Some websites might be forbidden, and knowing the website history of a client might basically send the clients to jail. So overall, this is a really critical information. And for this reason, some tools have been developed to hide this information, which website the client accesses to ISPs to attack her. And with Tor, because the packets go through all these layers of routing, the ISP is not able to know which website a client accesses based on the headers that it sees. But what recent research has shown is that this is actually not enough. By looking only at the timestamp and direction of the packets, an ISP can still know and predict with very high accuracy which website a client accesses. And to illustrate this, I show this very nice figure from the paper Website Fingerprinting at Internet Scale from 2016. And what this figure shows is simply along time, the cumulative sum of the packets where outgoing packets count as -1 and incoming packets count as +1. And this is very little information, and we see clearly in this figure that only with this very limited information, two different websites show very differently. And an adversary can, of course, differentiate pretty easily which trace corresponds to which website. And of course, this is only a simple example with two websites, but what has been shown is that it is possible to devise so-called website fingerprinting attacks that will extract features from this metadata, the timestamp and direction of the packets, and that will apply machine learning techniques to predict which website a client accesses. And these are very powerful attacks. And in one recent attack, such attack presented in 2018, deep fingerprinting, it showed that out of 100 registered websites, an adversary is able to predict with 98% of accuracy, so close to perfect accuracy, which of these 100 websites a client is accessing. And this is not only the case in this small closed world experiment. What has been shown is that this is a very practical attack, and in a more realistic open world experiments, similar precision can be achieved. So the title also mentions multihoming, so now I'm going to say what multihoming is. And multihoming simply refers to the fact that a client can access the internet with two different networks, two different ISPs. And this is something that is already widely used. Anyone with a smartphone is actually multi-homed because it has access both to Wi-Fi. It can access the internet with Wi-Fi through a public Wi-Fi or home Wi-Fi, and with the cellular connection 4G. And this will typically come with two different ISPs. And the smartphone is one example, but even a client with a laptop or desktop computer is also multi-homed because it can access the internet with a public Wi-Fi, for example, and with his or her home network through Ethernet, and again with typically two different ISPs. Or another example is a smartphone with a dual SIM, which can access two different ISPs with the dual SIM smartphone. And another technique that has been developed is multipath. And with multipath protocols, the client can send and receive packets simultaneously from the two networks. So for the same website accesses, it can send some packets to one ISP, some packets to the other ISPs at the same time. And these techniques have been developed mostly for performance reasons. And what we look into today is whether this can help protect against the website fingerprinting attacks. And we use this system model where a client is multi-homed, has access to two different networks, and connect to Tor through a multipath Tor bridge that can support multipath protocol, like, for example, MPTCP, which is the most widely used multipath protocol today. And the adversarial model is as follows. We assume that the adversaries, so typically the ISPs, are local, which means that they're only located between the client and the multipath bridge, so the first Tor node, and that they're passive. They only see the packets. They don't try to modify or remove any packets. Just look at them. And the other assumption that we make is that the two adversaries, those two ISPs typically, are cost equivalent, which means that the client does not try to minimize the amount of traffic that it sends to one of the ISPs, for example, and also that they are non-colluding. So what this means is that the ISPs only see the packets that flow through their networks, and they cannot reconstruct the entire trace. They only see the partial trace that flows through their networks. So in this presentation, we will present results in the closed world experiment with 100 websites and an adversary trying to predict which of these 100 websites the client is accessing. But in the paper, there are more results in the more realistic open world experiment with similar conclusions. And we use two different types of data. The first one takes existing publicly available data sets and simulate our algorithms on these data sets. And we also show results with real data obtained with the proof of concept implementation that I'm going to present. And the main question that we want to answer here is how to split traffic between these two networks to improve privacy. And I will present a privacy protecting multipath scheduler, HiWF. And to illustrate the splitting schemes, on the right side, I will show typical traces that an adversary can see. And this is the same figure as I showed earlier, where along time we plot the cumulative sum, where we count +1 for incoming packets and -1 for outgoing packets. And on the left side, I show the accuracy of one website fingerprinting attack, K-fingerprinting, against the different schemes, and here against the baseline, which is when there is a single ISP, a single path, and it achieves above 90% of accuracy. And the first, the simplest splitting scheme that we can use is for each packet, we choose the ISP with probability 1/2. And the consequence of this scheme on the traces is that they will all be scaled by 1/2. But clearly, this does not help privacy because the adversary is still able to distinguish pretty easily which trace corresponds to which website. And this is what we see when we show the result of K-fingerprinting against this scheme. It achieves around 80% of accuracy. So clearly, this is not enough. And a second scheme that we can use it, this time we draw a different probability P per website access. And so to illustrate this scheme, I show this example where the client first accesses Google, and she will choose a probability 0.2 and send randomly 20% of the packets to one ISP and 80% to the other. And similarly, the bridge chooses randomly a probability, here 0.5. Then if the client accesses Facebook, 2 new probabilities will be used. And if the client again accesses Google, yet another set of probabilities will be used. So what this means is that for the same website, 2 different website accesses will correspond to 2 different probabilities. And so the consequence on the traces is that each trace will now be scaled differently. And clearly here, the traces are much more intertwined, the traces of the different websites. And this makes it much more difficult for the adversary to predict which trace corresponds to which website. And when we see the result of K-fingerprinting against this scheme, we see that it's now below 50%. But if we look more closely at the traces, we see that there are events like that where the line go down. And what this corresponds to is a long burst of packets in one direction. And here, because it goes down in the outgoing direction. And here we see that these events appear similarly on all the traces. So for the red website, they appear twice, here and here. And for the green website, they appear 3 times, here, here, and here. And the reason why they appear similarly is because we choose the ISP for each packet. And so if the burst of packets in one direction is sufficiently long, for example, I don't know, 20, 40 packets, well, with high probability, each ISP will see at least a partial burst, probably smaller because it will only see some of these packets, but still it will see the burst of outgoing packets each time one such burst is sent by the client or by the bridge. And this is something that we can hide with the next scheme. And this time we send a certain number of consecutive packets to one ISP. So instead of choosing the ISP for each packet, when we choose one ISP, we send a certain number of consecutive packets to this ISP, and then only we choose again the ISP to which we will send to. And so what this will do is that it will hide some of these bursts for the ISP. They will still appear, for example, here, because you still need to send them, but they might sometimes be sent entirely to one ISP, and so the other ISP will not see them, like here. And so what this means is that the adversary will have much more difficulty using these typical characteristics of the website to predict which trace a website corresponds to. And so what we see with this scheme, this algorithm, which we call HighWF, is that the accuracy of the attack is significantly reduced. And so this is what HighWF is, our multipass scheduler. For each website access, we choose probability P in 0, 1. And then while there are packets, we draw a certain number n following a geometric distribution with mean 20. And what we show in the paper is that the average value, 20, has no impact as long as it is within a reasonable range. Then we draw I, 0, 1, following a Bernoulli distribution with probability P. And then we send n packets to ISP I, and we repeat this operation while there are packets. And we can compare HighWF against other defenses. And what is important to note here is that our defense, HighWF, has no overhead. It does not add packet, and it does not delay packets. And in contrast, In contrast, other defenses, because they have a single path, have no choice but to either add packets or to delay packets, and so they cause an overhead, either a traffic or a latency overhead. And what we see that IWF with no overhead does better or similar as other defenses. So it does better than adaptive padding when looking at the deep fingerprinting attack, which is the attack that showed the best results against our defense. And it does similar to walkie-talkie, while walkie-talkie has an overhead of 30% in terms of both traffic and latency. So now let me talk about our proof of concept implementation. So we implement IWF, our scheduler, with an architecture with two different machines. One serves as the client, the other serves as the multipath bridge. And the two machines are connected with two different Wi-Fi links that serve to simulate the ISP link. And we add some delay randomly with typical figures for the delay between the client and the multipath bridge to make this architecture realistic. And then the multipath bridge connects to Tor. And the first thing that we need to verify is whether this has a performance impact in terms of download time. Because I've said that our defense does not add or delay packets, but it uses multipath. And so we need to verify that multipath has no negative impact in terms of performance. And for this, we compare our defense with three other schemes: single path TCP, and two multipath TCP scheduler, the default scheduler, which tries to minimize latency, and a round robin scheduler, with just choosing alternatively one or the other of the ISPs. And on the left side, we see the time to first byte, so the difference between the moment we send the first request and the moment we get the first byte of a response. And on the right side, the time to last byte, so the moment where we receive the last byte, so which corresponds to the total download time. And clearly what we see here is that our scheme, IWF, shown on the right side, has no impact in terms of performance, time to first byte and time to last byte. And the reason is that Tor typically is the bottleneck and not the access between the client and the multipath bridge where we use multipath. And then what we verify on these now real traces obtained with real implementation of IWF is that it does improve privacy. And what we show is that indeed it does. So with the three unprotected traces, or with single path TCP and the two default MPTCP schedulers, we see that the accuracy is above 80%, whereas our scheduler IWF had an accuracy below 50%. So to conclude, we have presented a practical defense with multi-homing, IWF. And what we have shown is two things. First of all, our defense requires a specific multipath algorithm to improve privacy. If we use out-of-the-box multipath algorithm, privacy is not improved. And also, what we have shown is that we can devise a practical defense without overhead. Here, our defense does not add or delay packets, so it has no overhead. And yet, thanks to the use of multi-homing, it offers a protection similar to that offered by state-of-the-art defenses. And also what I want to emphasize is that our defense is compatible with existing defenses. It does not want to replace any defense. In fact, what we show in the paper is that if we use our defense IWF in addition to other defenses, with the same level of overhead, we achieve much better privacy. So thank you for your time today, and I'm looking forward to any questions that you would have.